Hello there, Mr. Sutton bringing you this lesson on volume. As this title suggests, we're going to be finding volume using solids of revolution. So let's define what we mean by a solid of revolution. This is a three-dimensional object created when we rotate an area around an axis over an interval. So I think an example will help here. Let's say that we take the area between y equals 1/3 x minus 4, shown in the graph below, and the x-axis. So this area right in here, and rotate it over the x-axis itself on the interval from -6 to 6. So here's what this looks like visually. I'm going to rotate this around the x-axis, and as I do that, it carves out a solid object. This solid object here is our solid of revolution, and we're going to be finding volumes of these things today. At this point, let's talk about how we might go about finding volume using something called the disk method. So recall that to find area between curves, we chopped up the area into an infinite number of little distance strips and added all those distances together to get an area. Well, when you're finding volume, we're going to chop up a solid into an infinite number of area slices and add those together to get the volume of the whole solid. So you could think of a solid as just kind of like a stack of pancakes, and we're chopping them into infinitely thin pancakes and adding all those together to get the whole yummy solid. So in general, we can say volume then, since we're adding a bunch of things together, is going to be an integral along some interval of whatever your area is. Now, taking a look at our pancakes and our cross-section here, the area of a solid revolution appears to be a circle at this point. So we can use pi r squared and add all those pi r squareds together. The catch, though, and you'll see that I wrote a of x equals pi r squared, the catch is that we have to express this formula in terms of x, because we're integrating in terms of x going horizontally here, and we have this dx in here, so we need something with an x in it. Well, the radius itself is the distance from the axis of revolution to whatever your function is at each input value. So in this picture, for example, our radius would be this f of x function itself. But it doesn't have to be the function itself. I mean, if this was shifted up so that your axis was the line y equals 1, then it's just the function minus 1. It's whatever that distance is going to be your radius.
Now that we've got that background on volume, let's take a look at this problem. They want us to find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. So we've got f of x, we've got x equals 0, we've got x equals 9, and the axis of revolution is the x-axis here. So I think it's a good idea to draw this out on Desmos if you're able to access a calculator. Pictures definitely help you visualize the radius when you're going to be using your formula. So going to Desmos, let's see what we got here. So let me put in f of x, and I'm going to do this anyway because I'm going to use an integral later on. So we have 1 plus square root of x, and then we have x equals 0 and x equals 9. And if you want, you can also put in the axis of revolution as a line. It's just the x-axis though, so it's not really going to add anything that's not already there. So here we are. We've got this bounded region in here. So this is the bounded region that we're going to be revolving around the x-axis. So at this point, if we're going to be doing this, we need to get our area formula. In general, a of x is going to be pi r squared. So now we need to fill in what this r actually is. Now r is the distance from the axis of revolution to the outside of your bounded area. So in this case, we have a distance of, well, it's just going to be whatever f of x minus 0 is, so just f of x. This is giving us the whole distance here, so we're just going to do pi times f of x squared. So there's our area formula. With that in mind, pause the video and see if you can take this the rest of the way and find the volume from this solid of revolution. Okay, so in order to get that volume, we need to take an integral of this area along the whole length of this bounded area. So I'm going to say volume equals integral from 0 to 9, because those are my left-right integration limits here. And then we're going to just use a of x. I'm just going to literally write a of x dx because I've already defined everything here. And a of x depends on f of x, which is also already defined. So let's just go to Desmos to make all of this happen. So in Desmos, I'm going to have to put my area formula in. So let me go down to a new entry, and I'll just write a of x equals pi times parentheses f of x, close parentheses, and we will square that. Now I've got a of x defined. I can use an integral with it. So int, integral. And let me just go down so I can see all that. And we're going from 0 to 9. And a of x dx gives me about 268.606.
For our next couple examples, we're going to take a look at a different kind of situation, and that is when we have a situation like this, where, for example, we want to rotate this area around the x-axis. This is a little different than before because now we have a space right here in between our function and the axis of revolution. When there is a space between your area and your axis, like in here, you're going to get a different look when you rotate this thing. If we rotate this, here's what the solid would end up looking like. We're going to end up with a hollowed out look because we have this kind of empty space in the middle of our solid. So how do we deal with that? Well, let's take a look at the cross sections because that's ultimately what we have to add together to get this whole volume. Our cross sections are no longer circles. We now have kind of a donut-shaped cross section, which in math terms we're going to call a washer. So here's a representation of a washer. To get the area of this washer, we have to take into account that we now have an inner radius, which I'm going to call little r, and an outer radius, which I'm going to call big R. To find the area of just the donut instead of the whole circle, we need to take the area of the outer radius and subtract the area of this inner radius. So subtract your inner circle from your outer circle. Algebraically, we're just using circle formulas, so we kind of have so pi times big R squared minus pi times little r squared. That's one way you could find that area of the donut. But in practice, we don't like writing pi too many times, so we usually factor out this pi and write this as pi times big R squared minus little r squared. So this right here is our formula we're going to be using to start things off on all problems that have this space between our bounded region and the axis.
Now that we've gotten our introduction to washers or donuts, let's try out a problem that involves them. It's not obvious at the start of it that this problem involves washers, but you may find when you graph this out that they are helpful. So with that little hint, pause the video and try to find the volume from these curves and this axis of revolution. All right, let's see how that went. So going to Desmos, we're just graphing it. We have f of x equals square root of x, and we also have g of x equals x squared. Pretty innocent sounding functions there. And there is what I've got. If I zoom in a little bit, it's this little sliver of bounded area there. Now, because I'm going to need it for this bounded area, I need to know my limits of integration for this thing. So I'm going to also figure out where f of x equals g of x. And I can do that directly on Desmos. Just click on either function and click on the intersection points. So we got 0. Over here is 1. So those are also pretty innocent sounding numbers. At this point, we notice that our bounded area is not flush against the axis of revolution. The x-axis and the area here, there's some space between them. Even a little bit of space means that we're going to have to use washers as the model for getting the volume on this one. So for my area, I'm going to use my washer area. Again, that's going to be pi times big R squared minus little r squared. And for my big R, that's going to be the distance from the further away part of the bounded area to the axis of revolution. So this further away part up here, this was my f of x square root function. So I'm going to have f of x as my r squared coming first in this subtraction. And then for my little r squared, that's this inner part of the bounded area, the distance between that and the axis of revolution, which is just going to be this g squared, or this g function. So we're going to have minus g squared, g of x squared. And again, my limits of integration just from left to right, that's going to be 0 to 1. So I've got the integral from 0 to 1 of whatever this a of x stuff is that we've defined here. So let's go back on Desmos and put all of that in. So for a of x, I'm going to put in, what did I write here? We had, I'll just go over here, f of x squared minus g of x squared in there. So we had pi, parentheses, and then another parentheses for f of x, so I can square that, minus another parentheses for g of x, so I can square that, and then close the big parentheses. So there's our area function, which we don't really care what the graph looks like for that, but we are going to use it in our integral. And that integral is going from 0 to 1. A of x dx comes out to not a whole lot of area, 0.942 and some change. So that's actually our volume there. For our last volume example today, we've got something special for you. So still the same kind of setup. We want to take these curves, the bounded area, and revolve it around some specified axis of revolution. But take a look at this axis. It's not the x-axis, it's not the y-axis, it's the line y equals 3. So this is our first problem where we're not just revolving something around the x-axis. So let's go ahead and put this in Desmos and see what it looks like. So back on Desmos, let me clear out all that stuff from that last problem. We have f of x equals square root of x. And what else do I have? We have y equals 2, x equals 0, and we're going around y equals 3. Let me just move this so I can refer back to those. So I'm just going to write y equals 2. I don't really need to call it g of x. It's a pretty simple function. And let me also do x equals 0. I mean, that is just the y-axis. And let me see what I've got here. Let me just zoom out a little bit. All right, so it looks like this is the area that we're going to be revolving around something. And our axis of revolution, again, is this y equals 3. So let me put that in here. Y equals 3. And if you want to be fancy, you can go to this little gear and change the way this line looks just to help you visualize it. So if you click on this circle here, it lets you change a few things like the color, the width, or whether it's dashed. I'm going to make it dashed. And now when I look back at this, I realize that this is not actually one of the bounding curves, it's the axis of revolution. Just a little visual aid to help you out there. So there's my picture. There's my bounded area that I'm actually revolving, and here is my axis of revolution. So needless to say, this is going to require washers. We have this huge area between the axis of revolution and the bounded area. So we're going to use our washer formula. Oh, I should also figure out where my f of x and my y equals 2 lines are intersecting. It looks like 4, but just to be on the safe side, let me go back to Desmos and really be sure. Clicking on the square root function, clicking up here, yes, we are crossing at 4. And that kind of makes sense because the square root of 4 is, you guessed it, 2. So that is going to be our upper limit of integration. Our lower limit of integration is going to be the 0 over here that we're starting at. Okay, so again, we're going to need washers. So here's my washer formula. Now when you're finding big and little r, it's a little trickier because you're not using the x-axis anymore. So you can't necessarily just use these functions as they are because the functions by themselves don't necessarily represent how far you are from this axis of revolution. So just a little bit of a hint. Each radius is still going to be a top minus bottom distance strip. You still need to think of higher minus lower. So with that in mind, pause the video and see if you can take this the rest of the way. Alright, so for my big radius, that's the distance from the axis of revolution to the further away part of the bounded area. The axis of revolution is 3, and we're going to be subtracting this lower y value, which is always just going to be the f function. So 3 minus f of x squared, that's my first thing I'm putting in there inside this pi parentheses. Now for little r, Again, that's the shorter away distance. We're going to have 3 minus the inner part of the curve, which is always just the constant value of 2. So you can write 3 minus 2 squared just to kind of see where things are coming from, or yeah, you could have just simplified that right away. Dealer's choice. Either way, let's do our volume now. That's going to be the integral from, we said, 0 to 4 of, and again, just a of x dx. It's really nice not having to rewrite all of this if we've already defined it. So let me go onto the calculator and put all this in. So let's see here. We had integral. Well, actually, let's do our area formula first. So that was pi, parentheses, and we had 3 minus f of x squared, so another parentheses, 3 minus f of x, close parentheses, square that, and then we had minus 3 minus 2 squared. Seems kind of silly to write this, but just for the sake of showing you kind of something that works with any curves, 3 minus 2 and square that, and then close the parentheses. A of x is now defined. So let's go down to one more entry. We'll do integral. We said 0 to 4 of a of x dx, and that comes out to 25.133. So there's our volume for this solid of revolution. And that's it for this lesson. You can turn down the volume on YouTube now. Until next time, Mr. Sutton signing off.